Chapter 4, Probability. This chapter and the next will turn out to be a little bit harder than the other chapters for most of the students here. At least, that was my experience teaching this course for a number of years. There's no way around it, however. After all, this course is called Elementary Probability and Statistics, not just Elementary Statistics. In other words, you have to acquire at least a certain level of understanding and probability in order to pass and succeed in this course. This chapter is structured as follows, and as you can see, this is a long chapter. We have 6 sections here, and all those are important, maybe except for the last one, 4.6. So I'd like to save some time by moving into my notebook and relying upon it. I have a little bit more control here, so I'd like to save some time skipping some topics and cutting some corners. Also, at the same time, this way I can make this delivery a little bit easier to you. First, let's take care of some terminologies. Sample space. Here's one important term. What is a sample space? It's a set of all possible outcomes. So, for example, if you roll a die, sample space will be 1 through 6. If you toss a coin, the sample space will be H or T. Event. Any subset of a sample space is called an event. For example, if you roll a die, you can consider an event of even numbers or event of odd numbers or things like those. Mutually exclusive events. If 2 events have empty intersection, or if 2 events cannot happen at the same time, we call those mutually exclusive events. As a matter of fact, there should be a Y here. Sorry about the typo. Mutually exclusive events. For example, E is even number and F is odd number in a roll of die, then there's a good example of mutually exclusive event. E is an even number, F is, say, for example, 1 or 3. Again, there is a good example of mutually exclusive events. E is an even number, F is, for example, 1, 2, 3. In that case, no, because there is an overlap. There's 2. What is the probability of an event? If my sample space is finite, we simply take the ratio of the number of elements of the event over the total number. Now, if you have infinitely many elements in a sample space, you can count them all. In that case, you'll have to use some kind of measurement. We're going to talk about it in terms of an example. And first example goes like this. Roll a pair of fair dice. And we have a black die that can run 1 through 6, white die that can run 1 through 6, as you can see here in this table. And consequently, we have 36 possible outcomes. There goes my sample space. Next question. What is the probability that the total number of dots showing is at least 10? At least 10, so 10 is included. 10, 11, or 12. Here's an example of 10, 4 plus 6. Another one, 5 plus 5. Third one, 6 plus 4. 6 plus 5, that's 11. 5 plus 6, that's 11. And 6 plus 6, that's going to be 12. Add them all up. We're going to get 3 plus 2 plus 1, 6 out of 36. Simplified into 1/6. There goes the probability. Counting part is easy. Understanding at least, that's an important concept here. In contrast, what is the probability of getting number of dots more than 10? In this case, 10 is not included. More than 10, so it's 11 or 12. So how do you get that? There are 2 possible ways to get 11 and 1 possible way to get 12. So we get 2 plus 1, 3 out of 36. The answer is 1/12. Likewise, we can consider at most 10. At most 10, that means 10 is included. So 2, 3, 4, 5, 6, all the way up to 10. Count them all, you're going to get 33. Or, clever students will do something like this. Out of total 36, we did this computation for more than 10, then there were 3. So 3 of them are out of total 36, and then what you get, we get 33 over 36, which is 11 over 12, the same computation back. We can use complement event like this effectively. That's particularly effective if your event is rather complicated. Likewise, you can do something similar with at least 10 and less than 10. Less than 10, 10 is not included. At least 10, 10 is included, which means we have precise complement. If you count them all from 2 to 9, then you're going to get 30 possible outcomes. Or you can calculate 36 minus 6 and get 30. Either way, you're going to get the same thing. There are more examples, but I'm going to leave you with your textbook and then move into another different types of example here. What if we have infinite sample space? Kind of like this. Let's suppose we have a circular dartboard, and the condition here is a randomly thrown dart hits a circular dartboard. If it goes outside, that's out of consideration. We consider that it is randomly thrown dart and it hits the dartboard. So what's the total? Total? Well, do we count the number of points here? Oh, that's impossible because there are infinite many points. The same goes for the event. The square region, well, impossible to count. So how do you calculate the probability that the dart hits the inside of the square region? Picture that follows. Well, we have to use a measurement here. What kind of measurement? We're looking at two-dimensional regions, so we have to use two-dimensional measurement. In other words, area. Area of the square over the area of the disk. Area of the disk will turn out to be pi r squared if the area is r. And area of the square I claim as 2r squared. Why? Well, I'm going to leave that as an exercise to you. In the end, r squared canceled out when you get 2 over pi, which is approximately 0.6366, something like that. How do we get area of the square as 2r squared? Well, the answer key is posted here. If you open up, you see the answer key, but no cheating. And I want you to think about it before looking up the answer key. This notebook is posted in a Blackboard site, so all you have to do is download it and open up the cell, and you're going to see the answer, but please try to answer the question before looking up the answer key. Okay, we went through a couple of examples, and now let's consider some properties of probabilities. These are 3 fundamental properties of probability, especially when my sample space S is a finite space. First, for any event, the probability is between 0 and 1. So 0 is impossible, almost impossible. 1 is absolute, almost absolute. If you like percentages, then it could be written as 0% to 100%. Personally, I prefer decimals, but if you use percentages, I'll accept those. Next, probability of an empty event is 0. Probability of total is 1. Well, that's pretty clear too. The total is always 100%, and nothing is nothing. Or, this may be overkilling, but here it is. A certain event must take place if you're going to measure the probability, but empty set is nothing, so what is probability of nothing takes place when something must take place? That's of course 0. And probability of S is probability of something taking place when something has to take place. Of course, that's 1. Maybe that's an overkilling. 0 to 100% argument will be perfectly fine. The next one, the probability of disjoint union, where 2 mutually exclusive events, will be sum of those probabilities. This union notation with this plot thingy here represents mutually exclusive union. Not just A and B what am I talking about? Well, not just A or B, but A or B where A and B is impossible, kind of like that. As a matter of fact, let me go over to chapter 3 and briefly show you a picture, kind of like this. This is an example of mutually exclusive events. When A and B are mutually exclusive, as you can see, no overlap, then the probability of this disjoint union is the sum of the probability. By the way, we are going to come back and discuss this in a little bit more detail in chapter 3. Right now, just stick to these three fundamental properties. With these three properties, we can deduce another interesting property, the property about complement event, because if you take A or not A, then it will be total, no matter what event you select. Something must take place, or the other must take place, of course. Consequently, if you flip this probability of A to the other side, you get this formula. Probability of the complement is 1 minus probability. For example, if you're going to calculate the probability of getting an ace, when you roll a die, what's the probability of getting an ace? Getting a 1 when rolling a die. And that's the same as 1 minus probability of getting something other than 1. The left-hand side is 1/6, right-hand side is 1 minus 5/6, right? Okay. That's what complement is all about. I have plenty of time left, so let me show you the picture of complement from section 3 of this notebook, kind of like this here. A is blue, a complement is everything other than A, which is pictured in red here. So they add up to the whole space 1. The final topic here is the odds. Okay, I admit it, this is not as important as some of the others, but our textbook discusses, so let's talk about it a little bit. Odds in favor of A is defined as probability of A to probability of its complement. A or not A versus not A. Odds against A is vice versa. For example, what is the probability and what is the odds in favor of an ace? Odds in favor of an ace when you roll a die, that is equivalent to, what's the probability of getting an ace? 1/6 when you roll a die. What's the probability of getting the other event? Is 5/6. And this proportion 2 is nothing more than fraction here. This one is fraction. So we have cancellation. Denominators just cancel each other. We have 1 to 5. Likewise, we can calculate the odds against A. Against 1, that is 5/6 to 1/6. Simplifying, what do you get? 5 to 1. At the end of our textbook, at the end of chapter 4.1, it talks about law of large numbers. It's an optional topic, so I don't want to emphasize it too much. It's basically this: if you repeat the same thing over and over and over again, eventually you're gonna get the expected value. For example, if you roll a die over and over and over again, and the proportion of an ace showing up will go pretty close to 1/6, And that kind of thing is the law of large numbers.